Welcome to this webcast. My name is Taro Eichler. I'm Market Segment Manager for Wireless Communication, and I would like to explain a little bit regarding millimeter and terahertz wave technologies and applications in the next 35 minutes. Currently, network operators worldwide are rolling out 5G, and the first step is enhanced mobile broadband. The next step for the next years will be vertical industries, so that they will drive 5G evolution. One of these bodies is, for example, the 5G AA, the 5G Automotive Association, or 5G ACIA, the 5G Alliance for Connected Industries. But 6G research is already starting now in industry and academia as well. So there's some technologies already identified, but these are all candidates, of course. Supermassive MIMO could be one, AI, machine learning for optimized networks, and sub-terahertz waves so are definitely a field which is maybe the most concrete. Everybody is working on in this direction. And another interesting aspect could be for security, so quantum key distribution using single photons to transmit data, because single photons cannot be copied. This kind of communication cannot be eavesdropped and is therefore intrinsically secure. So that may be a component, and many more are being discussed as well. ROHDE is active also in 6G research. So one of the activities is regarding terahertz channel sounding or terahertz communication at high frequencies. So we looked at 300 gigahertz, for example, in a cooperation with Fraunhofer institutes. I will talk later on about that. Let's have a look at the spectrum for 5G and beyond. If you look at the upper graph, then on the very left side you see the 5G FR1 spectrum with the aggregate spectrum of 1.3 gigahertz. In this area also lies Wi-Fi and LTE, of course. Then we have the 5G FR2 frequency spectrum. This is dark blue, going up to 52 gigahertz. Then if you go even further, so the lower part up to 52 gigahertz is basically the area for 5G. And if you look beyond 52 gigahertz, then this is an area which includes potential new bands, 5G bands, and also the 60 gigahertz unlicensed spectrum. So it's so part of this from 60 to 90 gigahertz is the so-called E-band. So this area is considered for 5G evolution or 5G plus. If you need higher bandwidth, and this is of course the case if you want higher data rates, in the case of 6G, then we need to look even to higher frequencies beyond 100 gigahertz. And here you see the D band in the area of 150 gigahertz, then the H band around 300 gigahertz. And the World Radio Conference already has identified bands in this H-band or at frequencies beyond 275 gigahertz, which could be potentially used for the future. And this is also one of the main research area. So the H-band frequency and the D-band frequency in the 150 gigahertz. So depending on where you look in the electromagnetic spectrum, there are various applications for which these frequency can be used. Starting on the left, we see, for example, the radio waves. This is in astronomy, but also broadcast, radio and TV. Going to higher frequencies is the area of the cell phones. Then we already there at the mmWave and terahertz region. So the terahertz region is considered to start at 300 gigahertz up to 3 terahertz. But some people also say it's between 0.1 terahertz, so 100 gigahertz up to 10 terahertz. So it depends. Yeah, in that area, one application is terahertz imaging, what we will talk about today as well. Then going to higher frequencies in the infrared region, then infrared thermal cameras, of course. Then later, so at higher frequencies is the visible light region. then ultraviolet region, which is used in medicine a lot, and X-ray imaging to even higher frequencies, and gamma rays, which is used for cancer therapy, for example, because it kills living cells. One aspect which determines how terahertz waves behave is their interaction with matter, and that's what we want to have a look at quickly. Here in this graph, you see the frequency and so the terahertz region. Basically here in this picture, it's shown from 0.1 terahertz, so 100 gigahertz, up to 10 terahertz. And in this area lie, for example, the rotation transition, so rotational transition of molecules. Here in this picture, you see, for example, a water molecule, then bond vibrations, stretching, and phonons. So these are lattice vibrations. So, and terahertz waves have certain properties. So, for example, terahertz waves can penetrate through materials which are not transparent for other parts of the electromagnetic spectrum. Packaging materials, for example, as plastic, ceramic, and so on. And it's also the energy is very low, so it does not induce any chemical changes or structures in the chemical structure, changes in the chemical structure. And also it can be used to create images and transmit information. That's what we will have a look at today. The big question is how to generate terahertz radiation. And there are several possibilities. So here again you see the spectrum. One way is to do up conversions coming from the lower end of the spectrum. The other possibility is coming from the higher end of the spectrum to do down conversion. And each of these ways has its advantages and disadvantages. So if you look at the up conversion, then there are electronic sources. For example, there are multiplier chains. It's also what we do a lot. Then there are RTDs, so resonant tunneling diodes, transistors, and so on. The advantage is it's compact, it is at room temperature, but at some point there's a bandwidth limitation and the efficiency is limited. Coming from the upper part of the spectrum, optoelectronics, what you can do is, for example, you can create a beat signal with two lasers and a beat signal, then mix it on a photodiode, so it's so-called UTC photodiode, and this is connected to antenna and then transmit terahertz radiation. It is tunable because the lasers are tunable. It is at room temperature, it's also good, but the power is limited and the efficiency as well. Then there's a way to, and this has evolved in last years, to directly generate terahertz radiation. And one of these possibilities, which I quickly talk about next slide, is the quantum cascade laser. And there are other ways using nonlinear optics, which also have less efficiency, molecular lasers, which are very inefficient, but the power is pretty much okay. But the problem is sometimes, for example, in the QCL case, you have to use cryogenic equipment, which means it's very bulky and you have to cool it to very low temperatures, maybe like 50 Kelvin. The terahertz region is still an area where it is difficult to efficiently generate radiation. That's why it has been termed the terahertz gap. Here in this picture, you see an overview. It's the output power versus frequency. The frequency in the terahertz region, for example, between 1 and 10 or 0.1 to 10 terahertz. And one sees the different technologies, for example, like QCL, like a quantum cascade laser, or other mmICs and other technologies. And what it becomes apparent is that the power goes down tremendously in the area of the so-called terahertz gap. This is now improving, so there are some technologies promising, but yeah, that's still the current status. One interesting example which has developed in the last years is the so-called quantum cascade lasers, where you have a semiconductor superlattice And in this lattice, here, for example, shown in the picture is a so-called quantum well. And you have, instead of intra-band transitions between different bands, such as for optical laser diodes, here you have an inter-subband transitions because the energies are quite low in the terahertz regime, and to get laser radiation. But this is improving a lot, but there are also other ways to create terahertz radiation, which we'll talk about later. So already demonstrations have been done at high frequencies, for example, at 300 gigahertz, point-to-point transmission for backhaul, for example, with a transmission rate of 100 gigabit per second. This has been done in the group of Ducournau in France. And this is was a demo at the so-called Terahertz Dates in Dunkirk in 2017. So the transmitter is at TX here, and the receiver is at a distance of 750 meters. And well, you have to very precisely align transmitter and receiver, and but you could get 100 gigabit per second transmission. So that's quite remarkable. And still, although it is in a harbor, and on the left side here you see the atmospheric absorption, which increases the frequency, it was possible still under these circumstances also to get a sufficient transmission. We talked about the application of high-speed communication. Now let's have a look at other applications such as non-destructive imaging, for example, for security checks and material analysis. On the left side, you see a picture or a photo of a man with the newspaper, for example, and on the right side, you see the same man standing, but this picture was made with a terahertz image. Strictly speaking, it's not terahertz, but it was at 94 gigahertz, but still it's already in a higher frequency region. And well, I mean, is visible, for example, this knife. So that could be one application. And I will also show actually a product from ROHDE and SCHWARZ, which does the same thing. Another application is the analysis of molecules. So here on the right side, you see a terahertz spectrum of a sample of diclofenac acid. It's the chemical name for Voltaren. Voltaren is basically a painkiller, and terahertz radiation can distinguish between two of it different chemical forms shown on the upper part and the lower part. So this just should underline that, well, for these large molecules, for example, this is pharmaceutical molecules, terahertz spectroscopy is a way to distinguish these, because they just lie, or these kind of different chemical compound differences just lie in this frequency region. Radiometer Physics is a company which also belongs to ROHDE and SCHWARZ. It has specialized in the past on radiometers, but also has other products such as Doppler radar and many more. So also very active in satellite communication, or components for satellite communication. This product now is made for investigation of clouds and cloud formation, but also, for example, quantitative analysis of or estimation of precipitation, such as rain and so on, cloud particles. And we will have a quick look at that. Here just shown some application examples where at different sites it is used. Quick remark, it operates at 94 gigahertz, so it's already in the higher mmWave region. With the cloud radar, you can analyze the different levels of clouds. For example, here, high-level cloud layers, mid-level cloud layers, low-level cloud layers, and precipitation. So that is, for example, rain. And on the right side, you see also different altitudes. Again, for example, ice formation, ice particles, and so on. So a very detailed analysis of depending on the height. Here's another interesting picture on the left side. You see, for example, again, small ice particles, which, and because in radar you use also Doppler, so you can also measure the velocity of the particles. Yeah, if they're just at a very low velocity at the same height or dropping. And for example, you see also in the cloud formation, for example, these updrafts, but also droplets here in the lower part. Droplets, this is, for example, rain, and they fall faster. That's why they're in a different color, and this you can distinguish. On the right side, you have examples where you can see turbulences, for example, and again, also rain. ROHDE has entered the area of millimeter wave imaging some years ago, and now there's a product, or since some years, there's a product so-called QPS, a quick personal security scanner, which is used at airports. And this operates between 70 and 80 gigahertz and can create a three-dimensional picture. In the airport, only the avatar is shown as here on the picture, if there's something suspicious detected. So this security scanner operates in a way here. On the right side, you see these so-called squares. These are modules, each containing each row contains the order of 90 antennas. So in total, the whole system has 3,000 antennas, transmit antennas and receive antennas. And it's a kind of three-dimensional tomography which is done. Each transmit antenna irradiates at a certain time and successively, and the receive antennas, 3,000 receive antennas, they take a picture or phase coherently measure the reflected waves at the same time. Yeah, so you get a lot of data, and this needs, of course, to be processed. But here you have the specs again: 70 to 80 gigahertz operation range, resolution is about 2 millimeter. And the peak power is very low, it's only 1 milliwatt. This picture shows or illustrates the concept again. So 1 TX transmitter irradiating the device, whatever, this could be the body or some other part, and the reflection is recorded by the receive antennas. And yeah, you can reconstruct the three-dimensional image from that. And here's a picture of the gun, for example. On the right side then is the reconstructed millimeter wave image. Actually, this technology is also used, for example, for radome testing. There's another product, the QAR, to look at the homogeneity of radomes, because this is critical for radar. And here's another picture which shows you the three-dimensional nature of the picture which was generated. Another example of a picture which underlines the really high resolution which you can get. Now in the last part, let's have a quick look at channel measurements. That is one activity which is usually done very early in the development of a new standard. So why do we need channel models? Yeah, and the reason is explained in the slide, that usually if you do link level simulations, yeah, for example, if you develop a new physical standard, then it always starts with a channel model, because you have to simulate or test how your new physical layer would behave under certain channel conditions. Yeah, this could be dynamic channel conditions or static or quasi-static. But this is the reason why channel models are important and always an initial stage of a development in a new standard. And especially in the 5G early beginning, millimeter waves were new because, well, the frequency range was extended up to 50 gigahertz. Now people are considering up to 100 gigahertz. And for beyond 5G, even beyond 100 gigahertz. So you have, in addition, you have a three-dimensional, for example, 3D beamforming, yeah. So, and other behavior in this new frequency range, which is not yet completely understood. So that's always a start for a new, standard development. How do we do channel measurements? So it is also called channel sounding. This term comes from sonar. I think it's a quite similar principle, for example, from a ship, or you have a very short pulse, acoustic pulse sent out, and then you measure the reflections from the ground, I mean like from the seafloor. You get a picture of your surrounding environment by the reflections. In that case, of course, it's the source and the transmitter and receiver is at the same place. In the case of channel sounding, you have here two different places. This is shown in this picture: transmitter on the left side, receiver on the right side, and in between you have the channel, which could be buildings, trees, and so on. So what you do in the beginning is send a very short transmit signal, and this is a channel sounding sequence you usually use. It is modulated signal, very short, and then you measure the time delay. The first, what you get is shown in light blue, is a line of sight, so the direct path, and it has a certain delay because of the speed of light to your time zero. So you measure time delays, and you have another reflection here shown in red, for example, reflection from another building, and so on. And then you get in the time domain a kind of all the reflections from your original short signal. Here the channel sounding setup is shown. On the left side you have the transmitter, on the right side the receiver, and in between the radio channel. The sounding sequence comes from the vector signal generator, and the IF is then fed to the Terahertz transceiver. It's up-converted, and with an additional input of the local oscillator from the SGS. In addition, you have the 10 MHz reference for frequency synchronization, and the time reference, a very precise. So this contains a rubidium clock, because you need to measure on the nanosecond level time delays, absolute time delays. On the right side, you have the receiver setup, which is basically symmetric. You have a spectrum analyzer to collect the data, and again, a time reference. Our initial measurement campaigns were in factory environments, actually now factories in Teisnach and Memmingen, at frequencies 28 GHz because it's new for 5G, and also 67 GHz because it could be important in the future, and 3.7 GHz because it is the frequency which is used, for example, in Germany for private networks in factories. So the environment is new. That is why 3GPP had a focus on this kind of environments, and it is also discussed in 5G ACIA. So we contributed with inputs to 3GPP last year. Here this measurement shows an example from one of the factories. What is quite specific for this kind of environment is that you have this after this line of sight. So the first peak is the line of sight peak, the direct path, and then you have a very long shoulder because in a factory you have a lot of metallic objects, and at this frequency 28 GHz, it's a very small wavelength, and almost everything reflects. And in addition, what you can see here is that this small circle, this shows the angular distribution, from where the reflections come from. And in the lower part is the waterfall diagram. You see the distance between the transmitter and receiver is continuously increased from 3 meters to 727 meters. So that's why you see the line of sight path moves farther and farther away. The distance, the time delay between the transmitter and receiver is getting larger and larger. But what is interesting, you get also another pattern. One of the reflections is coming closer and closer the farther you go away. So this is a back reflection from the wall. ROHDE and SCHWARZ has different research activities towards 6G at high frequencies, sub-terahertz frequencies. So one of them is channel sounding. This is in cooperation with the Fraunhofer IAF, so it's Institute for Applied Physics, and the HHI, Heinrich Hertz Institute. So in this case, the Fraunhofer IAF contributes with the indium gallium arsenide mmWave technology, so basically the Terahertz transceiver. And well, this transceiver covers a rather broad range, around 300 GHz. and can be used for transmission experiments, so using new waveforms, but also for channel sounding as we use it for. And here you have a picture of this transceiver. We did experiments indoor, for example, looking at reflections. Here in the upper part you see some example, a reflection from a wall or reflection from the opposite wall, and also attenuations of different objects. Yeah, here you have some kind of plastic cover where you see some attenuation, some other kind of cardboard box and a human being, but just to get an idea what the behavior of these frequencies is. This was another indoor measurement, so the channel impulse response again versus a delay in an indoor environment, also 300 gigahertz, and you see again the direct path, line of sight, and many multipath components, which is specific or which is general for indoor environments. So just to get an idea, in a wave, electromagnetic wave travels 30 centimeters in 1 nanosecond. So for example, the direct path, line of sight, this was the distance between transmitter and receiver was 4 meters around. And well, this is a start now of our research activities. So we will in detail now look at different environments and do further measurements to characterize basically the channel at 300 gigahertz and also in the future other frequencies like 150 gigahertz deep band. If you have interest in more details about these activities, please have a look at the following publications. So one is measurement and characterization of an indoor industrial environment at 3.7 and 28 gigahertz. So this is about the factory measurements, and the other is a terahertz channel sounding. So this we plan now to extend further in the next couple of months. With this, I would like to close the session and the webcast. Thank you very much for your attention and hope you tune in next time.